Hey, this is chapter 22. It's about cutting tool materials and cutting fluids, and we will be mostly talking about cutting tool materials, but less on cutting fluids. And you can see that you're responsible for all these subsections, and make sure that you also go through another section on metalworking fluids in chapter 33. Now, let me briefly start with the requirements in machining. So, what do we need to have in machining? First of all, if you want to start machining process, then you need to have some relative motion between the cutting tool material and the workpiece. If you don't have it, then obviously they will be sitting beside each other and nothing will happen. This is the first requirement. We need to have relative motion. And the second requirement is that the cutting tool material should be harder than the workpiece material. Otherwise, it cannot remove material. For instance, think about this this cutting tool material is made of PLA type of thermoplastics, and if I use it as a tool, try to remove material from this aluminum, it's not possible since aluminum is harder than this PLA material, and that's why we cannot use this plastic as a tool to remove material from the aluminum. So we can say that the second requirement is that the cutting tool material should be harder than the workpiece material. Otherwise, we cannot remove material. The workpiece material may remove material from your cutting tool material, which is another thing desired. So in summary, I can say that there are two main requirements in machining operation. The first one is we need to have relative motion between the cutting tool and the workpiece. And the other one is that the cutting tool should be harder than the workpiece material. And that's why we will spend some time on the type of cutting tool materials. You need to select the right cutting tool material for your application. And these are highly important since the cutting tool directly affects the quality of your machining, the time you are spending on machining process, the cost of your overall machining, since the time will affect cost, and also the cost of the cutting tool will directly affecting the cost of your resulting products. And as we have discussed in the previous chapter, the cutting tools actually are subjected to several things. First of all, due to the friction, we have high temperatures, and your cutting tool should be able to withstand to these high temperatures. We have stresses due to the forces applied energies on the workpiece. We have high contact stresses. Your cutting tool should withstand to these contact stresses. Then we have some rubbing due to the friction between the chips generated and the rake face of the tool, and also friction between the flank face and the machine surface. So we should be aware of these and then design and select our cutting tool accordingly. Now I will talk about some properties which we want actually our cutting tool material possess. The first one is hot hardness, and as the name applies, it's actually having hardness values even at high temperatures. So if your material has good hot hardness values, then it should maintain its hardness even at high temperatures during the machining operation. Besides hardness, it should also maintain its strength, maintain its wear resistance, so that machining will even be performed at high temperatures. And the result is that our cutting tool will not undergo any plastic deformation. So if your cutting tool material does not have any hot hardness values or low hot hardness values, then probably it will be deformed at temperatures around 200, 300. Let me discuss it in this figure. This figure is showing actually the machining temperature and hardness value, different hardness values, but it doesn't matter. They are almost the same. As you see, as the machining temperature increases, the carbon tool steel, which is the most primitive type of cutting tool material, its hardness is suddenly decreased after, let's say, 100 degrees. You see, after this point, we have a sudden decrease in terms of hardness. So I cannot say that carbon tool steels have high hot hardness values. It simply actually decreases hardness as the temperature increases. But if you look at other materials, for instance, the second type of cutting tool material, high-speed steels, They are a bit better than carbon tool steels. For instance, at 500 temperatures, 500 degrees, its hardness is quite acceptable. But if you, on the other hand, look at ceramics as one of the best ones, it can retain its hardness even at more than 700 degrees. And its hardness values much higher than the hardness of carbon tool steel, cast cobalts, and high-speed steels. So we are always looking for a cutting tool material whose hot hardness value is good, whose also toughness, impact strength is good, thermal shock resistance, chemical stability, inertness properties are all good. Let's discuss the second one in a detailed manner, toughness and impact strength. Why do we need to have good toughness values? Since in machining process, we may sometimes have interrupted forces, interrupted cutting operation. If that's the case, we will have such forces applied actually on the cutting tool material. So if your cutting tool cannot withstand to these impact forces or toughness is low, then probably we will have some chipping. The tips, the edges, corners of your cutting tool material will be removed, and we will finally break the tool, and we will need to replace the cutting tool. So that's why we want actually our cutting tool material possess these properties: high toughness, high impact strength. Another property we want our cutting tool material possesses the thermal shock resistance, so that during the machining operation we may have some rapid temperature cycling, which means that temperature might be, let's say, around 500 for 1 minute, and then for another minute it may be around 100. So that's why during this temperature cycling, the properties of our cutting tool material shouldn't be affected, and this is called as thermal shock resistance. Another thing we want actually is somehow related with the hardness is wear resistance, which means that it's quite difficult to remove material from surfaces of our cutting tool material. It's highly related with the hardness. Then the last property we want our cutting tool material possesses the chemical stability and the inertness is another highly important, since during the chip generation, if you have some chemical affinity with the cutting tool material, then these chips may go into the ray phase or even flank phase of the cutting tool material. And we discussed that the case while we were discussing wheeled up edges. So if you have an chemically inert cutting tool material and workpiece material, then probably you have no wheeled up edges generated. And this will obviously increase the life of your cutting tool material. So this is a kind of a summary. Hardness and strength are important, since if they're low, you cannot machine difficult materials, difficult workpieces. And impact strength is important, since you may have interrupted cutting operations, especially in specific machining operations. Your cutting tool material should be having high impact strength. Otherwise, it can easily be broken. Then regarding temperature cases, the melting temperature of our cutting tool material should be as high as possible so that it will not be deformed. Another thing, thermal conductivity should be higher so that the temperature actually, the heat generated will not actually stay in the same region. It will be dissipated, expanded, so that again we will not have deformation on the cutting tool. And with the help of these, the cutting tool actually will have good thermal fatigue properties. And in this chapter, we'll be discussing these materials. It's not listed here, but the most primitive one is the carbon tool steels. The carbon tool steels were the simplest, were the first primitive type of cutting tool materials. And as we have seen here, they easily reduce their hardness values after high temperature. So that's why actually people start to work on specific materials and try to increase the hot hardness values. You see directly we start with high-speed steels. It's a bit better than carbon tool steels. Then we have cast cobalt alloys, some carbides, coated carbides, some specific coated tools, then ceramics, cubic boron nitride. This is an artificial material. Then we have ceramics again, but this time we have specific coated ceramics. Then the diamond we have is the hardest material we know in nature. And lastly, we have viscally reinforced materials and nanomaterials. These are topics we are going to discuss. And as I mentioned, carbon tool steels are the oldest one, and people start to use them around 1880s. And they were used in main machining operations like drilling, tapping, broaching, reaming, and some other maybe simpler turning operations. But these days, we don't prefer to use them even in simpler machining operations. But you can still use them for wood machining, plastic machinings, but for other metals, difficult materials, these are not used since they have lots of problems. And after that, they start to add specific items, specific materials into the content of carbon tool steels, and with the help of them, they increase the tool life at even high speeds. Now let me go through these tables. This table is about values, numerical values of these properties. If you're interested, you can have a look at them. Let's start with high-speed steels, the primitive one after the carbon tool steel. This is, by the way, they are ordered according to the time actually they developed. So the last one is the one actually developed lastly, and high-speed steels were developed after carbon tool steels. And we are always trying to increase the hardness, as you see. It's always increased as we go from left to right. And this is a nice table actually summarizing the things, the properties we talked about in a moment ago with respect to these cutting tool materials. Please come to this table after we finish this chapter, after you watch all the videos and done with the remaining of this chapter. Make sure that you go through this table once again. And again, it's the same with respect to the previous table. We have the primitive one as the first column, then the mostly recently developed type of cutting tool material on the right-hand side. Let's have a look at the first property, hot hardness. As we discussed, people were always trying to find a cutting tool material having very high hot hardness values. And that's why throughout the history, they developed such cutting tool materials. And now we are making use of diamonds. And as you see, it has the highest hot hardness value. Then we have toughness and impact strength properties. They are highly related to each other, but they are inversely related with hot hardness value. If the material is harder, then I can easily say that its toughness is very low. It cannot actually absorb these high forces, and probably since toughness is related with impact strength, it cannot withstand to impact forces. So if you have such impact forces applied on a cutting tool, then probably if it's diamond, then you're going to break your cutting tool material. But if it's on high speed steel, then it's quite fine. It can withstand to higher impact forces. Then we have wear resistance. It's related with hardness. That's why it increases as we go towards diamonds. Then we have chipping resistance. It's related with impact strength and toughness. It means that it's quite difficult to actually remove little materials from the surface edges, corners of the cutting tool materials if they have good chipping resistance like high-speed steels. But it's quite worse in diamond material. You can easily remove little diamond particles by applying some impact forces. Let's have a look at cutting speed. This time it's inversely related with chipping resistance, but highly related with hot hardness. You can increase the cutting speed as we go towards diamond once again. But the thing is that the depth of cut of diamond cannot be too much. Even though the cutting speed is high, you can remove little material from the outer surface. But for the other ones, other materials, the depth of cut is not bad as diamond. It may be light to heavy, as you see. For all these, we have a depth of cut range and noted as light to heavy, which means that you may remove, let's say, 100 microns to some millimeters. It's all possible with other type of cutting tool materials. So what about tool material cost? Since diamond is quite rare material, its hardness is high. That's why it's one of the expensive cutting tool materials. And the most primitive one has the lowest cost, high-speed steels, and the other ones are in between. So we can say that tool cost is somehow related with the hardness. Then we have thermal shock resistance. It's quite related with the toughness and impact strength. If the thermal shock resistance of a material is higher, then as we discussed, it can withstand to temperature cycling cases, so that you can do some machining and then wait some time, do another machining. It's quite possible with these a bit primitive cutting tool materials. And that's all for the introductory part. In a moment, we will start discussing some other types of cutting tool materials.